We're going to start the course talking about what we know about global warming and climate change. I'd like to start by talking about this little picture we can see of the Earth with a fever. And we can think of the Earth as having a fever similar to the fever that we have when we're sick. When we're ill, we have maybe a fever of 1 degree above our 37 degrees normal temperature, maybe 2 degrees. If we get to 3 or 4 degrees, we'll be in hospital and it could be fatal. Well, today we can see the plot here of the fever of planet Earth. We can see that the average temperature, we'll talk about the average temperature later on, is around about 15 degrees. So we're much cooler actually than the body, but the temperature, the fever that the Earth has, is also on the order of 1 degree. In fact, the IPCC report in 2021 showed that we're 1.1 degree above the temperatures we had in the 1800s and about 100 years ago. And here on the plot you can see every red dot is the annual mean temperature from all the weather stations around the planet. But we don't measure everywhere. We don't have people living in the oceans, in the deserts, so there's some uncertainty here. And that you can see with these vertical lines on every red dot. When we go back 100 years, we have much more uncertainty. There are only maybe 5,000 stations we could use to calculate the global temperature. Today we have 10,000, maybe 20,000. We also have satellites. So today we have much better data. And with the good data, we see that the last few years are the warmest years we see on the planet. And nearly every year we're breaking records. The planet's getting warmer and warmer. As the data gets better, we're breaking records nearly every year. Now, if we try to fit the data, the red dots in the previous plot are now shown by black dots. If we try to fit this with a straight line to see what the slope, what the rate of warming is, we can do this over, say, the last 150 years, which is the red line. The blue line is the last 100 years. The orange is the last 50 years. And then the last 25 years in yellow. What we see is that the rate of warming is increasing with time. As we move towards the present, things are warming much faster, which is also worrying for us regarding global warming. If we look at the actual warming which is occurring for different months of the year, here you can see the hours on this clock are actually the months of the year, going from January to December. And the year is shown in the middle relative to the temperatures which were in the 1950s, 60s, and 70s. So in the beginning of the 20th century, the temperatures were cooler. And we can see that as this clock keeps going on to the 1940s, 50s, and eventually will go to the present, we're going with larger and larger radiuses, and the temperatures at all months of the year are getting warmer, and this continues until the present. And so we can see that it's not just the annual mean which is getting warmer, but the temperatures in every month of the year are getting warmer and warmer. And we can see that at the moment, again, we're more than 1 degree above the temperatures that were in the 1950s, 60s, and the beginning of the 20th century. We can see this also in 3 dimensions, this kind of funnel where we're going from the bottom in the 1800s, the end of the 1800s, to the present, and you can see the funnels getting wider and wider with time, and we've passed this 1 degree fever that the Earth has. Now, when we look spatially at the global warming, what we've looked at now is just the global mean, which is just 1 point for the whole planet. But when we look spatially, we can also see some interesting features. First of all, global warming isn't uniform. It's not the same everywhere on the planet. What we're seeing here in these 4 different images are the decades of the 1980s on the top left, the 1990s, the 2000s, the 2010s in the bottom right. And what we see more yellows and oranges. The scale here is what we call anomalies. Anomalies are the changes, not the absolute temperatures, the changes from, again, the reference period of 1951 to 1980. So if we have positive changes, which are the yellows and the oranges and the red, then it's warmer than it was in the 1950s and to the 1980s. And if we see blues and greens, then it was cooler in that decade than in the 1950s and the 1980s. And if you look at the bottom right, even in the last 10 years, well, in the decade of from 2010 to 2020, near Antarctica, you'll see a patch of blue, which means for that whole decade, there were areas on the planet which were actually cooler than 1950s, 60s, and 70s. But that doesn't mean that the whole planet was not warming. So when people talk about very cold winters and very heavy snowfall in a specific year, it doesn't mean that we can rule out global warming. Global warming is when the planet is warming, but we can have certain areas which are actually cooler than normal for certain periods. Something else we see here is that the warming is mainly or more exaggerated over the continents. So over the continental areas, we're seeing more warming than we're seeing over the oceans. And maybe the most interesting thing here is at the high latitudes, like around the Arctic, the North Pole, and starting to see that around Antarctica, we're also seeing an amplification of the warming. Much larger warming at the North Pole than we're seeing in the tropics. And if we look just for these 2 years of 2020-21, again, we see a lot more oranges, yellows, and reds than we see blues, showing that we have generally global warming. The number on the top right shows the global warming in temperature, so 0.93 degrees relative to 1951 to 1980. And again, we see the very high warming, say, in Siberia, northern Canada, and around the North Pole, which I'll explain in a few minutes, and we'll learn about it during the course. Now, some of the skeptics and deniers of global warming say that the warming we're actually seeing is simply because we're measuring in our cities, which are growing and growing with time. And as cities grow, we remove the vegetation and we're building roads and we've got lots of cement. And this results in what we call the urban heat island. And so the actual cities are causing this increase in the temperature. Well, to show that that's not correct, we can look at what's happening in the oceans, which are 70% of the planet. And here we can see a plot of the planets, the warming from 1880 to the present, where the y-axis is latitude, so from the North Pole to the South Pole, looking at all the oceans. And again, the color here represents the change in temperature relative to that control period of 1951 to 1980. And again, we see that before the 1950s, we see some blue colors, which the oceans were a little bit cooler, but in the last decades, we can see lots of yellows and reds, showing again that the oceans are warming as well. It's not just in the big cities, not just over the land. Everywhere on the planet, we're seeing the warming of the planet. Now, in this animation, we can see actually both the continents, the spatial distribution of the continents, and each circle here is for a different country in the world. And this is an animation showing the relative warming again of each, or cooling of each country around the planet. The colors are obviously cooler than our reference period in blue, and if it's warmer than it was in the 1950s, then they're red. And the size of the circle says something about the intensity of or the cooling or the warming. So Israel is somewhere you can see in the middle towards the right. And now we're in the 1930s, we're still before this reference period, so we're seeing some blues, some reds, a mixture around the planet. Once we go into the 1950s, 60s, and 70s, we'll see, again, a mixture of the colors. And once we go further to the 1980s, 90s, and the 2000s, we'll start to see more reds and oranges, and showing that in every country around the world, we start to see the warming around about the 1980s. And the more we go into the future or closer to the present, we see more reds and oranges. And this will end in, I think, 20 or 2021. Where all the countries of the world are showing global warming. There's not a single country which is still blue on this plot. And if we look at Israel, it's at this stage about 1.4 degrees above the temperatures from our reference period from 1951 to 1980. Now, if you don't believe the data, which shows us that the globe is warming, you can simply look out your window, maybe not in Israel, but in other parts of the world, in Alaska, in Peru, in Europe, and we see that glaciers are melting all over the world. Here we can see images from exactly the same spot, but in 1920 compared with 2005. In Peru in 1978 compared with 2011. And if we go into Alaska, the McCarthy and the Muir glaciers, we can see pictures here, 1909 compared with 2004, and 1941 compared with 2004. If we look around the world, 90%, if not more, maybe 95% of all the mountain glaciers are retreating. They're getting smaller. And the only way we can explain this is that the air is actually getting warmer. Now, besides mountain glaciers, we have ice in different places on the planet. And first we'll talk about the sea ice. So sea ice is ice which is actually floating on the ocean. And at the bottom we can see that most of the sea ice is really in the northern hemisphere around the North Pole. I should point out there's a significant difference between the North Pole and the South Pole. In the North Pole, we have no land. There's only ocean. And on top of the ocean, we have ice floating on the oceans. The South Pole in Antarctica, we only have continent. We have rock and mountain also covered in ice. But this results in very different climates and different problems in the north and the south. In the bottom left map, we can see this red line, which represents the spatial extent of the sea ice at the end of the summer, so after we've had the maximum melting during the year. This is for the period of 1979 to 2000. And then we can see what happened in 2007 and then in 2012. We're seeing a dramatic decrease in the amount of sea ice covering the North Pole. And this has implications into the warming of the planet. And this is also related to what we saw earlier of the amplification of the warming at the high latitudes. We'll talk about this also later in the course, specifically related to the regions of the Earth covered in ice. But something we have to say about the ice, although we have measurements now, which you can see here, dramatic decrease in the extent. So this is a plot showing the area coverage of the North Pole, how much is covered by ice at the end of the warm season, so at the end of the summer. And we can see that every summer there's more and more melting and less ice covering the North Pole. But something important to know is that although the ice is melting over the North Pole, it's floating in the oceans. And we can look at this example, this animation, and you can do your homework at home. You can take your Coke or your glass of water and put some ice in it. Once the ice is floating in the water, it doesn't matter whether it's solid or whether it melts and it turns into water. And so this means that actually the ice which is floating on the oceans in the North Pole, when it melts, it does not influence sea level rise. It doesn't change the sea level rise, unlike the continental ice, which we'll talk about in a second, which does result in sea level rise. So the melting of the sea ice in the North Pole has very important implications for the climate, but it doesn't impact the sea level rise. Now, how do we actually track the ice sheets and how much is melting? As similar to what I mentioned before, that not many people live over the oceans, in the oceans, not many people live on the ice sheets. So we have some very clever satellites now which are flying around the planet. One of them is called GRACE, which actually measures the gravity of the Earth underneath the satellites. Now, we would think gravity doesn't change really, and gravity is the force that the Earth pulls on the satellite. But when we have 3 or 4 kilometers of ice above Greenland or above Antarctica, that's a huge amount of mass which is pulling on the satellites. And if that ice is melting, then we reduce the amount of mass which is pulling on the satellites. So the satellites are actually, these are 2 twin satellites which are a few kilometers apart with a laser beam between them. And as they go over the Greenland or Antarctica, there's a change in the pull on one of the satellites relative to the other. And from this small change, we can say something about the change in the gravity, the change in the mass, and hence the change in the amount of water which is being melting and flowing into the oceans. So here we can see on the top plot the changes from the satellite data of the ice over Greenland, covering Greenland. And this satellite's only been up from about 2002, so we don't have data before that. But we see that there's this constant decrease going until today. And if we look at the slope of this curve, it's approximately a loss of 275 gigatons, 1 billion tons of water every year are being lost from Greenland. And basically, when it's flowing from the land to the ocean, this water is directly influencing sea level and increasing the sea level. Similar in Antarctica, we can see this little animation. On the right, you'll also see the change of the color, where we're having melting, more melting and less melting over Antarctica as a function of time. But Antarctica, we can also see with the same satellite, we see this decreasing trend. We're having less and less mass of ice above Antarctica, which means more and more ice melting and going into the oceans. Of Antarctica, because it's a lot colder than Greenland, the decrease is less. It's about 149, 150 gigatons of water, 1 billion tons of water every year going into the oceans. But both Greenland and Antarctica, which are the main sources of ice on planet Earth, are melting very quickly and are causing sea level rise. And this is what it looks like if you go visit Greenland in the summer. You'll see these melt ponds on the top, and you have these waterfalls which will drill a shaft all the way through the ice, 2 or 3 kilometers waterfall. The water eventually makes it to the bedrock and will flow then to the sea. And all of this water then is going into the oceans to influence sea level rise. So how do we track the sea level rise? So here too we have satellites in space, a radar satellite, this one which sends a beam down to the oceans. It gets reflected back. By the time of the reflection, the beam coming back, you can calculate how high the sea level is. You have to do this over many days and maybe weeks to get rid of the influence of waves in the ocean. But using these measurements over years, we can actually track what is the relative height of the ocean relative to some reference. And we see now we have this data from the 1990s. And again, we see from the 1990s to the present that sea level is rising quite rapidly. The slope here doesn't sound like much. It's about 3 millimeters per year globally. But the predictions are that if we keep on going in this direction, we may get to about 1 meter rise in sea level around the whole planet by the end of the century. The different colors here simply show different satellites because a satellite has a lifetime of maybe 5 years and has to be replaced. You do cross correlation so we can get long-term trends in sea level. So sea level is rising. Well, there are lots of things we know now about the climate system. We're saying what do we know, and here you can just see 10 different factors which all point to the fact that things are getting warmer. If we look at the 7 parameters shown with the white arrows, we see that we expect them to be increasing in the atmosphere if the climate's warming, and they are increasing, in fact. If we're looking at the temperature of the sea surface, the temperature of the air, the humidity in the air because of more evaporation in a warmer planet, temperatures of the ocean. And we also, if we look at the black arrows, there's certain parameters which we expect to decrease in a warmer climate, like the decrease in snow cover, decrease in glacier and sea ice, and all of these are also occurring.